Let's complete our notes for Lesson 6.4, Day 1. We ended yesterday by graphing the parent function for sine. Using the information for a and b, let's create our new table for y equals 2 sine pi over 2x. So we know we have y equals, and then we have the 2 from our a value, and then we have pi over 2 from our b value. So remember, our b value is going to give us our new start and our new end point. So we're going to start at 0 and end at 4. Now, just like our parent function where we have 3 points in between, we need 3 points in between here as well. To figure out where those points are, we kind of just talk about, or we find the halfway mark. So what I mean by that is what's halfway between 0 and 4, that would give us 2, and that goes right in the middle. And then we split that up again. Halfway between 0 and 2 is 1, and halfway between 2 and 4 is 3. So that wasn't too bad to get us to that location for those input values. Now remember, our outputs, our a value is 2. That means we're going to multiply all of our outputs by 2. So all of these outputs, and this is just like what we did in that first day's lesson, we're going to multiply them all by 2. So 0 times 2 is 0, 1 times 2 is 2, and then we're back at 0. Negative 1 times 2 is negative 2, and then we're back up at 0. Now what I want you to do is plot these 5 points. Let's see, we have 0, 0, and then we're going to go 1, 2. So these are nice because they're integer ordered pairs, so they're super easy to graph. 2 back down to 0. At 3, we go down to negative 2, and at 4, we're back up to 0. So that ends a lot faster than the parent function does. To continue the pattern, every time I go 1 to the right, I'm going to change by a factor of 2. And that'll put me all the way to the end of the graph. And now we need to do the same thing, but in the other direction. If I go 1 to the left, I'm going to count down 2, and then go back to 0, and then again 1 to the left, up 2, back to 0, and so on. I have points to go from negative or from the left to the right side of my graph. I'm going to now go ahead and draw the curve through those points. When you're finished, hopefully your graph looks something like this. Now to look at our kind of transformation rules, we said the graph stretches vertically and compresses horizontally. And I believe it did both of those things. Let's try our last example. Our final example, y equals 3 sine 2x. The first thing you want to do is describe the transformations. Starting off with that 3, that's our a value. And an a value of positive 3 is going to stretch the graph vertically. The b value is 2. Now remember the rule for b. It always does the opposite kind of what we think it's going to do. 2 is a number that's greater than 1, and that actually compresses the graph horizontally. So very similar to what the last example did. Let's figure that out with our new input and output. So our new start, we're going to take 2, or the bx, or 2x, and set it equal to 0. Now to get x by itself, we simply divide both sides by 2, and that cancels, and we get x equals 0. So it's the same start as before. And again, this won't always happen, but it's nice when it does. To get the new end point, we're going to set 2x equal to 2 pi. And now when we divide by 2 to get x by itself, the x's cancel on the left and on the right, and we get x equals 1 pi, as our end location. So instead of ending at 2 pi, we're going to end at 1 pi. This definitely compresses our graph. Let's go ahead and start with our parent function, y equals sine x, and then we'll graph our new transformation. We have our x and our y, so we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. Well, those pi's aren't trying to get in there, are they? There we go. That looks a little bit better. Now our sine function, sine of 0 is 0, and then it goes 1, 0, -1, and 0. Go ahead and sketch the graph all the way from -4 pi on the left to +4 pi on the right. Once you've graphed that, press play, and we'll look at what happens with our transformation. Your graph should look something like this when you're done, sketching all the way from left to right. Now taking a look at our new table, we have y equals 3 times sine 2x. Now remember, the 2 affects our input and the 3 is going to affect our output. So our input is going to start at 0, but remember, end at 1 pi. And we have to have 3 ordered pairs in between. So this is where things get a little bit trickier. Halfway between 0 and 1 pi is 1/2 pi, or pi over 2. So that isn't so bad. But now we have to think about, well, what's halfway between 0 and pi over 2? Well, half of pi over 2 would be pi over 4, or 1/4. Half of a half is a fourth. So that would be pi over 4. Then to be even a little bit trickier, halfway between 1/2 pi and 1 pi is 3 pi over 4. So we're just kind of finding those even divisions from left to right. All right, and we'll have to figure out how to graph those on our graph as well. All right, the value for y, we're going to multiply by 3 because a is 3. Oh, this is going to make things really big, isn't it? So we're going to take all these values right here and multiply them by 3. So we'll go 0 up to +3, 0 down to -3, and back up to 0. So I'm going to zoom my picture out to show you how to graph those unique teeny tiny inputs for x. If you remember from yesterday, these divisions, I know, I'm sorry, they're so hard to read, but I wanted to give you a graph big enough for the bigger transformation for that that horizontal stretch yesterday. So that first dash mark is pi over 2, and that second dash mark is just 1 pi. So if we want to figure out where pi over 4 is, that's going to be right in the middle. 3 pi over 4 would again be right in the middle. So I'm going to draw little dash marks, kind of all the way through in the middle, because that's where we're going to plot additional coordinates. We need to do the same thing, oh boy, on the other side. So I'm going to slide this over and do the same thing. This graph is going to look so different from its original parent function. All right, let's get all those, try to get it as consistent as possible. Let's get all those little dashes in there. Oh boy, there we go. That's a lot, isn't it? All right, let's take a look at what the shape of our graph is going to look like. Go back over here. Oops, I didn't mean to draw that. Sorry, that's not what the shape of our graph looks like. Hang on. Oh, I know, you think I'd made a video before for this, but not the case. All right, so 0, 0. We're going to start there. That's going to be our beginning value. And then pi over 4 is that first little dash mark. We've got to go all the way up to 3. And then pi over 2 is back at 0. 3 pi over 4 is down to -3. And then pi is 0. That's just one loop. And now we get the joy of continuing this on. So to do that, I'm going to go 1 to the right. I'm going to go up to 3, back down to 0, and continue that pattern. It's a nice consistent pattern. All the little dash marks are either at +3 or -3. Whoops, that's not the right spot, is it? Here we go. Let's fix that. And then right at the pi/4s and pi/2 rules, you're right on the 0 of the graph. And now we need to do the same thing on the other side. Go ahead and connect those dots and then press play, and we'll draw the sketch of this very compressed graph. And there we have it, all the dots from -4 pi to +4 pi. Your goal is to connect them with a smooth curve. Go ahead and try that, and then press play, and we'll be done. And there we have the shape of the graph for y equals 3 sine 2x. It definitely stretched vertically and compressed horizontally by a factor of 2. So these are the rest of our notes for lesson 6.4, day 1. Please take a picture of yesterday and today's notes and submit it on Schoology for credit.